Hello, physics students. So today, since I have a meeting, we're going to do this a little differently. We'll see how this works out. So you should have, and I think I'll probably have given this to you already. If not, this will be on the front of my desk. But it's terminal velocity. It's entitled Terminal Velocity Scenarios and Verification. And so what I'm going to do is kind of walk you through this as if I were in class. I'll ask you to, you can do this in individually, or you can do this in teams of two, or however you want to break up. If you want to throw this up on the big board and kind of watch it all together, it doesn't matter. I don't mind at all. Let's start off by giving whatever you think your definition of terminal velocity is. So in this, you may or may not have any prior knowledge of terminal velocity. Maybe you do. And so jot down your thoughts on what you think might define terminal velocity. I'm going to hit the pause button now. And you'll also want to hit pause and then continue on whenever you have your definition of what you think terminal velocity is. All right, so I'm going to continue on now. If you don't have that definition done, then hit pause again and do that. So a lot of folks will think of terminal velocity as being, and really by definition, it's the fastest an object can travel through a medium. Now, you usually think of terminal velocity as when things are falling. And so if I drop something off of a very tall building, what's the maximum velocity that it would achieve under just the force of gravity? And so that's one way of thinking of terminal velocity. We could also think of terminal velocity as I could throw an object. So if I throw an object, for instance, if I try to throw a piece of paper, like a wad of paper, I may, when it leaves my hand, it may be going faster than terminal velocity. And immediately what would happen is it would start slowing down to match that terminal velocity because of a lot of different factors that we'll talk about in a little bit. But for our purposes, we'll kind of think about terminal velocity as dropping an object, whether that's a skydiver out of a plane, whatever that might be. So let's kind of treat terminal velocity as that. So it's really the maximum velocity that something can achieve falling under its own weight. Let's move on to this part A, this little activity that I have here. So I'm going to actually move me way over here. I want to be able to see this chart here. So part A here says, what factors do you think might affect the theoretical? There is a formula we'll talk about in a little bit. What do you think might affect, what factors, what variables do you think might affect the terminal velocity of an object that we drop? By the way, there really are 5 key factors in the theoretical equation. Please do not Google the theoretical equation. I'm just asking you to try to do this based on your knowledge. So see if you can come up with what you think 5 different factors might be. Then once you have that factor, so let's suppose that you think the day of the week might affect terminal velocity. That's obviously a very silly answer. Then for that factor, I want you to think, does it have a direct or indirect effect? Now, remember, our direct effect would mean if we increase your factor, so as we increase the day of the week, do you think a direct relationship would be that would increase terminal velocity, or would it decrease terminal velocity? So the direct would mean that you would go, one goes up, the other goes up. Indirect, as one goes up, the other one goes down. So we're really thinking about your factor here. So as we increase your factor, what's the effect on terminal velocity? So I want you to hit pause, brainstorm those with either your partner or with yourself. See if you can come up with 5 without Googling it. And then we'll move on. All right, so hit pause now. All right, so I'm back again. So hopefully you were able to come up with at least 2 or 3 things that you were able to use. Now, let's suppose that we have the following objects were dropped from a pretty tall building. So 25 meters, that's going to be about 75 feet, which would be about a 5 or 6 story building. So we're pretty tall here. Just throwing a cat on here, although we'll talk about that in a moment, or you'll see something. It's interesting. It would land on its feet, by the way. There's actually a pretty interesting physics behind cats and falling and landing on their feet. So let's take these following objects. We got bowling ball, ping pong. You can read there. So I just want you to make a guesstimation. What do you think? So do you think if we drop these at 25 meters, so pretty tall building, would they achieve their terminal velocity? Okay, falling about 75 feet. So again, about a 5 or 6 story building. So go through there. You can just say yes or no, yes, no. Think about those a little bit, and then come back to me, and we'll be ready to move on. All right. So then the back of this. So this is the back, and I don't even think I can make myself shrink down. I can make myself shrink a little bit so we can still kind of see that. So I've given you some different things here. This is again Wikipedia, and again I know that we've talked about if Wikipedia is a valid source, and my argument is it is a valid source for at least gaining general knowledge. It is a big research project. So you notice that there are footnotes here. So there's documentation for everything that's stated here. Wikipedia entries are nothing more than a giant research project that's can be done by many people. So I know that some of my colleagues may have a different opinion of Wikipedia, but I think for scientific entries, it's pretty solid. It really is. There a lot of textbooks are when you look at the entries, they look a lot like a textbook would, and they're pretty solid entries. I will say that I will stand up for Wikipedia and the not really crowdsourcing, but the concept that they follow. So what I would like you to do is I would like you to read this first section here. So this first section, and then what I would like you to do, then there will be some questions that come with this in this quizzes lesson, and you'll answer those questions, then you'll move on to the next. So I'm going to divide up the video into multiple sections. So, all right. So read this first section. When you get down here to Mr. Eckert finds this entry pretty interesting below, then you can stop. So just read down here to convection currents. Okay. All right. So that should have given you an idea of what some of the different factors are that affect terminal velocity. And so now let's move on to this interesting one here. I find this part pretty interesting. It talks about some different specific animals and people falling and things like that. So if you could read this next section, I find this go read the rest of this page. I find this last part pretty interesting by this biologist, J.B.S. Haldane. It's an interesting quote that they used here in the Wikipedia entry. So read the rest of that, and I'll be back with a few more questions, and then we will move on. All right. So now we're ready to kind of talk about the equation for these things now. So mathematically, terminal velocity, this is the overall equation. So v sub t, so the terminal velocity is equal to the square root, this big giant square root of everything to make the math work out, 2 mg, so 2 times mass times gravity, divided by, now, does anybody remember that Greek letter? So it looks like a P. Does anybody remember from our Greek letters? I'd be impressed. It's rho, actually. So rho times A for area and coefficient of drag. There's another coefficient in there. Luckily for us, it defines everything down here. Now, I do want to talk about the units that we would use for these things. And these units are very important. So as we're doing calculations, you'll be doing them accurately. So I'd ask you to jot these in. I just remembered. So this handout you don't have yet. So because I didn't want you to have this ahead of time, so I will have this on the front table. Grab this and then be able to use this for the rest of the presentation. So I'm sorry that I'll kind of backtrack on that. So go grab that, and then we'll go back there and we'll fill in the units of these various variables. All right, so our v sub t, as it turns out, the equation for that is eventually going to, or not the equation, but the units that we want to use when we're plugging things in, or what we'll get, are meters per second, which is probably pretty predictable. M is going to be the mass of the falling object. So what do you suppose we're going to use there? Yes, kilograms. So I'd put kg out here, or you could make a little table out here, however you want to do it. So our terminal velocity is going to be in meters per second. Our mass is going to be in meters. Our gravity is going to be meters per second squared. Okay, so using gravity. And then coefficient of drag, unitless, no units there. Density. Now, density is going to be an interesting one. So density, when we're doing this, is going to be And all of a sudden, I should have looked this up ahead of time. So I believe our density in what we have here is going to be in kilograms per meter cubed. So in my board back here, I'll write this out. So this is a weird density. We usually think of density was actually done in grams per milliliter, which is really grams per cubic centimeter. And if you can't see this, I apologize. I'll make this a little bit larger at this point. So there we go. And so generally we think when you did densities like in physical science, it would have been grams per milliliter. To make the math work, so which I said is also grams per cubic centimeter. So a milliliter is a cubic centimeter. So a gram of water, we had 1 gram of water, it would weigh 1 gram would be a cubic centimeter. So if we had like a little block, almost like a dice size, maybe a little smaller than a die, that it would be exactly 1 gram. That's actually how we defined how they came up with the idea of gram is an invented mass. And they just they used water, which has a density of, they just find it's going to have a density of 1. They could have easily said, hey, we're going to use some other liquid. Let's suppose we're going to use 100% alcohol to base things. And if they did a 1 gram, 1 cubic milliliter of alcohol, 100% alcohol, and they said that's going to be 1 gram. Well, it would actually make water weigh a little bit more because alcohol has a lower density. But so anyhow, they could have really used anything they wanted to. They could have said a block of aluminum, 1 cubic milliliter, 1 cubic centimeter of aluminum is 1 gram. Then everything would seem to have a much less mass than it does today because that would have been heavier. So anyhow, it would have changed things, but they used water for that. So for our purposes, though, we're going to use these kilograms and kilograms because, hey, mass above was kilograms. So you see why the units need to work out. And then we're going to say meters cubed. So which is a big unit. So if we think of like a cubic meter would be like a meter by a meter by a meter. So that's a big chunk of volume. That's a big volume. But really when we get down to it, density is really nothing more than mass per volume. And that's why this unit would work out. So there's the unit that we're going to use for our equation in this. All right, so let me come back here. And sorry about that if you're getting seasick. Let me make myself a little smaller here. And so the coefficient of drag, the density here, projected area. So what do you think we're going to use for the area? So when we'll talk about projected area, what I mean here in a moment. And so what do you think is going to be the units of our area? Now I'll give you a hint. You think back, we were using cubic meters here. Area is two-dimensional. So you probably maybe predict meter squared. So meter squared will be the units that we're using for area. Now, it's important to understand that it's projected. Now, when I say projected, so I'm going to guess, do I have any kind of a spherical object here? I don't. I'll be right back. All right, I'm on my way. Didn't prepare for this very well. All right, so let's suppose that we take this softball. Now, when this is going through the space, when it's falling, only half of it's really going to come into contact with the air. Now, what's the surface area that we actually use? Do we figure out the surface area of a sphere and use that? Which I think if memory serves me correctly, that the area of a sphere is 4/3 pi r squared, I think is right. But we actually don't. What we do is when they say projected area, what they're really thinking of this is in 2 dimensions. If you look at the end of this, so what you're seeing here in 2 dimensionals, because this is 3 dimensional because it's coming out at you as well, but in 2 dimensions, this is a circle. So for that area, it would be nothing more than what the circle would be that we're actually looking at here. I think I just got off the end here. So if I were to draw this in a circular pattern, so if I were to draw this circle of the ball, okay, so that's pretty much the same, then I would actually just be figuring out the area of that. If it were a piece of paper falling through the air, then it would be the surface area of this in meters cubed. So if I were doing something really small like this, it's going to be really small because this is only going to be, it's going to be an awfully small projected area. So that projected area is really thinking about the surface area of a it's a three-dimensional object being changed into 2 dimensions. And so we wouldn't account for any curvature or anything. We would just think, what shape would that make if we were projecting its shadow? So you think about it, it's like the projected shadow. So if I had a really bright light, whatever shadow would be projected onto the wall, that's the projected area. Okay, so think of it as kind of being like surface area, but it's this projected area. So we'll try to stick with some pretty good objects that are round, which is pretty easy to do circles, or something that's flat. Except for you, we are actually going to figure out the surface area of a person and figure out what you would actually fall through. Now, these coefficients of drag, now these are something you'd have to be given. And so if we actually, and I'm going to scroll down, and you might have already seen because it's on your handout, there are several coefficients of drag that I've actually given you here. I've pulled these again from where else? Wikipedia. But they were cited. These are right in textbooks. So I like this graphic over here. It's kind of showing you these values. And they look a lot like coefficient of friction values, which they're really the same. They are these coefficients. Now, these arrows, this is showing you that this would be the way they're falling through the air. So from all of these, they're all falling to the left. So if you turn your computer sideways, these would be falling. So when you do the area, it would be the area that would be coming into contact with. So this one would really be, this would be strange. This triangle falling would be kind of hard to come up with its projected area. But think of everything as falling to the left, so to speak. Okay, and we can see these coefficients of drags. Now, it might make sense if we compare this rounded objects. So this one is sort of like this. Or in fact, yeah, if it's like a half of this ball, and it's dotted line because it's open. So this would be an open hollow hemisphere versus a solid hemisphere falling. And notice that the coefficient of drag is actually a little bit less for this hollow object. Now, if it's falling the other way and the flat side is falling, notice that, so this 1.17 would be like a thin disc falling horizontally. Here's a rounded object, which is exactly the same. Then we start getting like parachutes. Down here towards the bottom, these are almost like parachute values. These are some huge drag. And you want parachutes to have a huge drag to really slow a person down. And when you think about somebody parachuting out of a plane, terminal velocity is really important to them. And so you want that terminal velocity to be really low when you're getting ready to land onto the ground. And then I've given you some other values here that they've kind of described things, and there's some vehicles in here that they do actually can figure out that coefficient of drag for objects. And race cars are all about coefficient of drag, of making that coefficient of drag as low as possible. The reason that Prius and a lot of these really fuel-efficient cars, the shape that they are, is because they have, looking at other sedans, they have really low coefficient of drag. So you look at the shape of a lot of high-efficiency cars, they have a lot of the similar shapes. So if you look at, like, for instance, if you look at the Toyota Prius that I have, its shape is really similar to the hybrid that Honda makes. And even if you look at the shape of my Bolt, it has a similar kind of shape. It's all about aerodynamics and trying to, better fuel efficiency or better battery life. So just be aware that that's how we work those things that we have up here. So hopefully that helps with the different units. Now, then what I've given you, and I think if you look at the back or the side or however the handout worked out, I'm just looking at things here. I want you to, so I'm going to put several objects. I'm going to put several objects in a basket or in something. They'll be laying around the room here. And what I want you to do is I want you to take, and again, you can work individually with somebody. I want you to figure out what the terminal velocity, and I'm going to have some scales. I'll put the triple beam balances over for you to use for mass. We're going to go old school here. If you're not sure how to use those, then ask a classmate. I showed some classmates last week on how to do those. And so the tricky part will be doing that projected area. So since these are spherical, just pretend that they are flat objects. Figure out okay, area of a circle. Area of a circle is area equals pi r squared. Now radius is half the diameter. Yes, you knew that, but remember to do it in meters. So they're going to be really small numbers. So make sure you're doing that in meters. Make sure you have mass in kilograms. We're going to assume, since these are spherical objects, when you do your coefficient of drag, which one do you think we should use here? So if we're doing spherical objects, which coefficient of drag do you think we should use? And hopefully you figured out 0.47. That's what I would use for the terminal velocity of that. Okay. Um, and so that's kind of where I think you'll get to today. Now, if you get further than that, and I don't even remember if I printed this thing off, this next one, but I think I'm pretty good with you stopping once you finish that task and you've done a couple of those different objects. Then, yeah. Oh, I will tell you my bowling ball. I'm going to put the bowling ball back there. The bowling ball has a mass of, I believe, 12 pounds, 12 labels, LBSs. And so if you need to convert that, then to figure out what its terminal velocity would be, because it's really stinking high, then you can do that. So, all right, hopefully you found this little lesson on terminal velocity interesting, and we can apply this, and we will either tomorrow or the day after, we're going to actually calculate the terminal velocity of some objects, or at least an object, and we'll see how closely it compares to the theoretical value. All right, thanks for watching, and I will see all of you tomorrow.